The visible universe is held together by an invisible glue. It's called the strong nuclear force, and it's the exact mechanism that binds atomic nuclei, creating the stable matter we see all around us. Yet, for all its importance in keeping reality intact, our mathematical models of exactly how this force operates at the most granular level are surprisingly incomplete. To figure out what we're missing, physicists use stripped-down test subjects to push these models to their limits. The ultimate test subject is the lightest known exotic nucleus, called the Hypertriton. While a standard stable hydrogen nucleus might have just a single proton and a neutron, the Hypertriton adds a third exotic particle to the mix, a lambda hyperon. Because it consists of only these three interacting particles, the Hypertriton lacks the noisy complexity of heavier elements. It acts as a highly sensitive stress test for our baseline physics theories. But relying on this exact particle created a major roadblock, a long-standing scientific contradiction known as the Hypertriton puzzle. For decades, physical experiments produced completely conflicting results about exactly how tightly this specific nucleus was bound together. Researchers testing the particle using older methodologies, like emulsion tests and heavy ion collisions, could not get their math to agree. The resulting values for the Hypertriton's binding energy were scattered all over the map. Without an accurate, agreed-upon measurement of the simplest exotic nucleus we know of, our broader understanding of the strong nuclear force was stuck in limbo. Breaking this deadlock and finding the true mathematical value meant physicists would have to build entirely new machinery to observe something that is practically impossible to catch. The core physical hurdle preventing a clear measurement is time. A single hypertriton exists for only a few hundred trillionths of a second before decaying and vanishing completely. An international research team known as the A1 collaboration, working out of the Mainz microtron facility in Germany, set out to definitively settle the debate. To capture that incredibly fleeting lifespan, the team utilized an experimental infrastructure of staggering scale and complexity. At the heart of their operation is a massive, high-resolution array of 4 interconnected spectrometers, specifically calibrated for exotic hypernuclear experiments. For this exact run, they also designed custom physical hardware, an unusually long and highly thin lithium target. The team strikes this thin lithium target with an electron beam. The unique geometry ensures that the particles produced in the collision suffer minimum energy loss as they travel outward toward the spectrometers. This highly specialized physical architecture was the only way to guarantee a level of measurement precision that could finally bypass the limitations of older setups. Even with this massive machinery, the team employed an ingenious methodological workaround. Because the Hypertriton dies almost instantly, they didn't actually try to measure the Hypertriton itself. Instead, they used decay pion spectroscopy. When the Hypertriton decays, it shoots out a pion. By determining the trajectory and energy of this ejected pion, physicists work backward to calculate the original Hypertriton's binding energy. To guarantee exceptional accuracy, they calibrated this proxy measurement directly against the already well-documented decay of another exotic isotope, hyperhydrogen 4. When the data finally came in, the results were definitive. The Hypertriton's binding energy was significantly higher than the accepted consensus. The A1 collaboration proved that the proton, neutron, and lambda hyperon are bound together much more tightly than any of the older, contradictory models suggested. By abandoning direct observation in favor of a highly precise proxy measurement, the team successfully cleared away decades of conflicting data. These new findings from Mainz are not an isolated anomaly. The higher binding energy aligns perfectly with recent heavy ion data gathered by the STAR experiment in the United States. This international consensus officially puts the decades-old Hypertriton puzzle to rest. The immediate physical implication of this data is clear. The invisible interaction pulling the exotic lambda hyperon and standard nucleons together is inherently stronger than previously theorized. Discovering a stronger interaction places strict new mathematical constraints on our foundational models of the strong nuclear force, forcing theorists to update their baseline assumptions. With this highly accurate baseline established, scientists are already beginning to theorize the existence of entirely new exotic systems, such as a hypothetical nucleus made of a lambda hyperon and 2 neutrons. By engineering a highly precise way to measure a particle that vanishes in less than a blink of an eye, physicists have permanently sharpened our picture of the fundamental forces holding the entire cosmos together.